So this is going to be the most involved part regarding the theory behind thermal and mechanical properties. I'm going to go through basically the numerical solvers that include the anisotropy, and that's mostly where the complexity comes from. So basically, once we have detected the orientation of our materials, what we basically are going to need to do is a tensor rotation. And this, by the way, you're not going to have to do this. It's done automatically for you by the numerical methods. So the tensor rotation basically aligns the local property that you are inputting inside the functions with the local orientation that has been detected. So in this case, I'm just showing basically a 3D voxel domain, and this is basically how, if you zoom in one of the inside the fiber, this is how it will look like. So basically what we are going through as a first step in our numerical solver is a tensor orientation to align the local tensor that a user would input with the local orientation. And this can be easily done just by multiplying it by a tensor rotation matrix. So then the two numerical approximations that we've implemented for the thermal conductivity and the elasticity are based on a similar numerical method. One is called multipoint flux approximation, and the other one is called multipoint stress approximation. So the first one goes like as I'm going to explain it now. So what we are basically solving, as Joseph mentioned earlier, in our conductivity simulations is basically just the divergence of the fluxes going to zero at steady state. So the three steps that are involved in a normal simulation is basically we give an initial guess, for example, in this case, going from a temperature of 0 to 1. And then we feed this temperature guess to a conjugate gradient solver, which converges our temperature, and then from which we can compute the converged fluxes, from which we can back out the effective tensor. So depending on what direction you're currently running, you're going to obtain basically a different row of that effective tensor. So the way that we approximate the fluxes, and we linearly relate them to the temperature at the nodes, this is what this is meant for, is by what is called the transmissibility matrix. So, and this is what the MPFA, so multipoint flux approximation, is about. And a similar approach is used for the elasticity as well. So if we just sketch out a 2D grid, in this case, we have cell-centered nodes. And so if I zoom in just four pixels in here, what the MPFA tells us is that we need to consider a control volume, which is in red, and an interaction volume that is in green. And I'm not going to go through the details of the mathematics for this, but the only thing that is important to know is that for this, the interaction volume basically enforces the continuity of fluxes and temperatures at the boundary points. So between different cells, we have continuity, and that's why we want to have a finite volume scheme that is as conservative as possible for the fluxes and the temperatures. So this is basically just explaining how you would enforce the continuity of fluxes and temperatures. You can create a local system of equations that can be inverted in order to obtain this transmissibility matrix, which relates your fluxes to the temperatures. So the similar approach that I explained in 2D can be applied in 3D. So for the multipoint stress approximation, which is very, very similar, what we're solving for is basically the divergence of the stresses, in this case, going to zero at steady state. So instead of an initial guess that is a temperature gradient, is instead a unit displacement. And so we feed this guess inside an iterative solver. In this case, we do need to use a more complex solver. In this case, we use the big G stab. And finally, this gives us the converged stresses from which we can back out the effective homogenized property. So similarly, I now have in the cell centers, we have displacements, which are vectors, instead of having just a scalar for the temperature in the MPFA. So it's a little bit more complicated to obtain the transmissibility matrix, which linearly relates the stresses to the nodal displacements. But it's a very similar approach where you enforce the continuity of stresses and displacements in the boundary points, which gives you a linear system of equation that is solvable and from which you can obtain this transmissibility matrix. So next, I will go into the verification and validation for both the conductivity and the elasticity. But first, I want to give a code example of both these capabilities. In this tutorial, I'm going to talk about some of the most important material properties that can be computed inside PuMA. Specifically, it will be focused on the thermal conductivity, both considering isotropic and anisotropic phases, and then also an example about the elasticity, which basically relies on a similar numerical method as the anisotropic thermal conductivity. So let me jump into the code and I will discuss while this is running. So first of all, I'm gonna import a sample of fiber form that is 200 cubed, as you can see up here. And then I'm just gonna, in this case, crop it so that it's 100 cubed instead. And this is just to show you how you would basically do this cropping operation. And then I'm rendering the contour of these cutoff values. So in this case, since I'm using the render contour, as you can see, I'm creating an isosurface that is triangulated along this grayscale range that I've decided. So I will close this and I will let the solver run through the function already. But then let me discuss about how you would basically assign the conductivities. So in PuMA, we have a class that is called isotropic conductivity map. So for running the thermal conductivity function, considering the phases of our sample as isotropic, you basically call this and then add materials to it so that you specify the grayscale range and then add what isotropic conductivity you want for that specific phase. Then the second one is instead 12, which is basically for the fiber phase, since I'm selecting a higher grayscale range. And then it's basically just as easy as calling this compute thermal conductivity, feeding the workspace and the isotropic conductivity map. And then you would basically want to select the direction that you want to compute the effective thermal conductivity and assign the side boundary conditions. So in this, selecting a direction of X imposes a temperature gradient of 1 across the X phases. And so it keeps those as Dirichlet. And instead it keeps everything else as symmetric. Since I put the side boundary conditions as S, you can select the iterative solver that you want. In this case, I put conjugate gradient. And then the solver has already completed actually, and the effective conductivity, which is basically the first row of the effective thermal conductivity tensor, has been output already. And finally in here, I'm just plotting the temperature and heat flux field that has been output as part of our function. So let me show you how the results look. In this case, I have the temperature on the left. So as you can see along the x-axis, we have a temperature gradient going from 1 to 0. And then on the right instead, we have the heat flux. So not much heat flux, and this is mostly because the fibers are seem to be more oriented along the y-axis instead. But as you can see, the higher heat fluxes go for the fibers that do connect the x negative phase and the x positive phase. So pretty interesting. As you can see, the temperature follow how the fibers are arranged. So I will close this and I'll comment this first example considering isotropic phases. And now instead I will consider the phases as anisotropic. So I will again import the sample, and in this case, instead of cropping, I'm rescaling it again just for showing you how you would do such an operation. So I will run this function again, and then something that is necessary for the anisotropic component is to compute the orientation of these fibers. So in this case, obviously, I'm basically assigning an isotropic phase to the air. This 0.0257 is the conductivity at room temperature for air, and instead I'm giving the fibers a conductivity that is cylindrically orthotropic. So along the fibers I'm giving it a conductivity of 12 and 0.8 instead across the fibers. So this is why we need the orientation. So as you can see, I'm actually outputting a rendering of the orientation that has been detected automatically using the structure tensor. So I will close this and let the solver solve for the effective thermal conductivity. And in this case, I'm computing it along the y direction, so it will be the second row of the effective tensor, and then again using symmetric boundary conditions. And in this case, since the MPFA, which is the numerical method that is used for computing the thermal conductivity for anisotropic phases, is more complex than the one that is used for isotropic phases, I need to use the big G stub, which is another iterative solver. So I will now let the solver converge, and then we will investigate together the results. Okay, the solver has now converged, and just FYI, I had to change, I had to rerun the solver so that this is correct. But let's investigate. In this case, this is the diagonal component, is the middle one, since we are on the second row of the tensor. And so here are our results for the temperature on the left and heat flux on the right. So as you can see, we have a temperature gradient along the y-axis, and so again the temperature has converged to basically follows the orientation of the fibers. And in this case, we have a very high flux for the fibers that connect from left to right this sample. So pretty interesting here. I will now close this one, and I will now run instead the elasticity one, which is a little longer. Comment the other one, and I will now rerun, close this one, and run the last example. So for the elasticity one, what I'm going to run is instead a sample of random spheres, and so in this case it's 100 cubed, and so I set also again the random seed so that the runs are repeatable. And in this case, I'm actually not treating the spheres to be solid, but I'm treating them to be the air phase, so everything else will be solid. And so as you can see, I'm binarizing this generated sample so that ID of 1 is given to the lower range. So in this case, what we get is basically a sample like this with spherical porosity instead. So one thing that is important for the elasticity is that there are no rigid body movements. So by rigid body movements, I mean basically floating unsupported voxels. Like for example, in this case, we could see these specific ones are just floating around without being supported. That would generate a singularity in our A matrix that we are solving for in the elasticity. So in this case, I've wrote a small function that is called remove RBMs, or rigid body movements. And so I will close this and let it run, and it will output re-render the removed RBMs sample. So as you can see up here, there are no floating voxels anymore. I will close this and let the solver run while I talk through it. So the first thing that we need to define is an elasticity map. So very similarly to the isotropic and anisotropic conductivity maps that we created earlier, what we want to assign now is instead the Young's modulus and the Poisson ratio for, in this case, for isotropic materials. We also have another option for passing an elasticity that has to be oriented with your phase in case it's orthotropic, or you can also give a complete anisotropic coefficient to this phase. So next, we feed both the workspace and the elasticity map inside the compute elasticity, and in this case I'm giving a direction of x, so I'm computing the first row of the elasticity coefficient, and then using symmetric boundary conditions. And in this case it's yet again different. The iterative solver that I recommend is called GMRes. The reason for the different solver is because the numerical method that I use for the elasticity is based on the MPSA, which is called the multipoint stress approximation, and it's basically a level up in terms of complexity with respect to the multipoint flux approximation for the conductivity. So I will now let the solver solve for the elasticity, and what it will give us is basically U, S, and T are the displacement field, the sigma direct stresses, and the tau shear stresses for this specific setup. So in this case, since I'm running the x direction, I'm imposing a displacement of 1 on the positive x phase, and then that's kept as with Dirichlet boundary conditions, and instead I'm using side symmetric boundary conditions. So briefly, these three fields are also going to be exported inside a VTI, which can then after be post-processed inside ParaView. But here I also prepared some plotting for showing the direct stresses, the shear stresses, and the displacement in several ways. So something that you can do is basically create just a PuMA workspace, and then fill in the orientation and the matrix as you can see down here, so that the render volume and the render orientation functions just work out of the box. I will let now the solver complete, and then we can take it from there. Okay, so the solver has now converged, and so as you can see, what it has given us is the first row of the 6x6 elasticity coefficient. So also the next part where I'm plotting it, I'm basically just building up. First, I'm rendering the orientation that is basically given by the displacement field. And so this is what I'm plotting in here, where I'm plotting a vector field. As you can see, you can barely see the porosity that is not rendered. So something else that I'm currently implementing is a function in PuMA to warp the domain, but it's not quite completed yet. So I would basically, for now, rendering it as a vector field, and you can see like what parts of the domain are basically displacing more than the rest. So if I then close this, and I'm gonna let the rendering generate the plot for the stresses, both direct and shear, and there they are. So as you can see on the top, I'm coloring the domain by the displacement in the x direction, and then the displacement in the y in the middle, and in the z on the right. And then the second row are all the direct stresses. So in the specific one that is interesting for this case is the x sigma direct stress, and as you can see, it's higher than the other two. And so finally on the bottom, you can barely see it, are the shear stresses. So some of the xz in this case, it's a little higher. So this completes the tutorial about the material properties, conductivity, and elasticity. Thank you for watching. I will now very briefly present about the verification and validation that we've been running for these two solvers. So there are more details in the papers that I referenced, but I just want to very briefly show you the results. And as you can see, the answer completely agrees with the analytical solution, our numerical answer. And then for the heterogeneous, instead, it's basically two materials having two different conductivities. And we also have an analytical solution for that. And still, our numerical answer agrees very nicely with the analytical solution. And this we also have for the flux. Next, I'll briefly share with you our validation again on some experimental values for ADEPT. And if you want to read more, here is a link to the paper where these results are discussed more in detail. But basically, we ran several different conductivity simulations for different configurations of ADEPT, which have basically different woven domains. And here are a couple of the candidates for ADEPT. Here is the 8-layer yarn, and instead here is a 4-layer yarn, and the different temperature fields that we obtain, as well as the heat flux.
Just for context, for people that are not familiar, what adept means is just a nickname for a type of woven material that that was used in one of the NASA systems, and there is a fairly solid database of experimental material properties that can be used to validate.
Mm-hmm. Yeah, thank you, Francesco. That's really important. So, yeah, we have basically benchmarked our runs against experimental values that were obtained for the different woven domains. Then something that I just wanted to mention is that something that is really hard to know experimentally is the conductivity of a single fiber. So again, in that paper, you can find a whole parametric study going from basically attempting to match the experimental values for the macro scale conduction across the weave by varying the local conductivity of the fibers. And so there is a whole parametric study that we ran in order to back out a single fiber conductivity that can match the experimental values. And then finally, you can, once you have the single fiber conductivity to plug in the conductivity map that is used in the solver, you can basically attempt to estimate the effective property for different weaves. So the next one is the verification campaign that we ran for our elasticity solver. Since there are not many analytical solutions available, what we did for this part is that we benchmarked against a finite element software called Codaster. And in this case, these are some of the results that we obtained, where I'm going to click through and you can see a very, very small change between our answer against the Codaster one, as you can see here, for the different stresses for this specific built-in beam case. This is instead a plate with a hole, which is another pretty commonly used engineering test case. And so the different stress results look very, very similar between PuMA and Codaster. And on the bottom, instead, it's a plate with a crack, where you obtain basically a singularity on the tip of the crack. And so at that point, we believe that our solver is basically being more accurate than the finite element Codaster one, because we are basically using a very conservative finite volume approach. So in the places where singularities like this arise, our solver, we believe, is more accurate. So one last slide from me is about an application case for the elasticity solver that we've basically been running for validating the solver for woven composites. And this is basically gonna be presented in a paper at the next AIAA SciTech by my colleague Sergio. So his application is basically studying a woven composite by investigating the porous phenolic resin that is used in between the toes of the weave, as well as then going another phase that is investigating is the intra-toe fiber packing and how the elasticity for this specific intra-toe fiber packing looks. And then this is important because then we are basically considering a woven unit cell. And so this intra-toe fiber packing elasticity is going to be an input for the toes that are, in this case, monolithic. They don't have porosity and they don't have every single fiber discretized. So here are some of the results from his study. And this is something that is going to be available online after the AIAA in January. And here is basically the results for different runs on the phenolic porous resin for different levels of porosity. And then on the middle is instead the unit cell for the intra-toe fiber packing with different levels of fiber packing. And finally, on the right, we have the woven unit cell for this specific 3D weave in the 3 direction, in basically displacing it in the X, Y, and Z in these cases. And these are the stresses that are obtained on the toes. So this concludes my section about the mechanical properties as well as the conductivity. I will pass now the ball back to Francesco and Joseph. And if anyone has any question, I'm more than happy to answer.
Yeah, Federico, just to complete, so most of the calculations that have been shown are again in the form of tutorials, right, in the documentation of PuMA. So if the participants are interested in any specific question, in any specific topic, we just recommend to run the tutorial and then maybe reach out to Federico and Joseph if you want to adapt it to your specific case or the specific material system that you're interested in analyzing.